This is Precalculus section 3.4 notes. Today we're going to begin by talking about complex numbers. A complex number is a number of the form a plus bi. A is the real part and bi is the imaginary part. And hopefully you recall that I is called the imaginary unit, and I represents the square root of -1, and then I squared is equal to -1. That we learned in Algebra 2. So for the next couple examples, we're supposed to determine the real and the imaginary parts of the complex number. So 7 minus 5a, the real part is 7, and the imaginary part is -5i. In number 2, 9i doesn't have a real part, so the real part is 0, and the imaginary part is 9i. And in the last one, number 3, 82 is the real part, and it doesn't have an imaginary part, so the imaginary part is 0. Now, number 2 here is kind of special because when you don't have a real part, when you just have the imaginary part, that is called a pure imaginary number. Because the real part equals 0. So we have some examples where we're going to do some work with complex numbers, some simplifying by combining like terms, some multiplying, that sort of thing. So in example number 1, we're just adding two complex numbers together. So in this case, remember they both have a real part and an imaginary part. So we are going to combine the real parts together. So we're going to add 8 plus -7. And we're going to combine the imaginary parts together. So we're going to add 6i plus 5i. So our answer is going to be 8 plus -7 is 1, and 6i plus 5i is going to be 11i. So our final answer has a real part of 1 and an imaginary part of 11i. In example number 2, these two binomials are being multiplied together, so this is going to be a FOIL problem. First times first, 2 times 8 gives us 16. Our outers, 2 times 5i, gives us 10i. Our inners, -3i times 8, gives us -24i. And then our lasts, -3i times +5i, gives us -15i squared. Now we need to simplify. Our inners and our outers are like terms. 10i plus -24i, that makes -14i. We have this real part of 16. Now this -15i squared, remember, I squared is equivalent to -1 from the top of our notes. So anytime you see I squared, you should always replace it with -1. So this right here is -15 times -1, which becomes +15. So we end up with 16 plus -14i plus 15. We can combine the 16 and the 15 together. So our final answer is going to be 31 plus -14i, or 31 minus 14i. In number 3, we have to think about the fact that underneath the radical we have a -6. Now, up until this point this year, we would just say that's not real and we'd stop and we'd walk away. But now that we're reintroducing our imaginary numbers, we can go ahead and we can simplify this a little bit further. So you could think of this as having 6 times -1 underneath the radical, right? Well, the square root of 6 part we can't do anything about, but we can pull that square root of -1 out and we can call it I. And since this is an even root, technically speaking, if we were solving an equation, then we would need to put a plus or a minus in front of it. Now here we're not solving an equation, we're just simplifying. Since this root does not have a plus or minus in front of it, I think we can assume that they just want us to give the positive root. So I'm going to say that the answer here is I square roots of 6. Same thing with number 4. Now number 4, we've got that negative 1 under the radical, and then we also have that 49, which 49 is a perfect square. That is 7, and the square root of negative 1 is I. So this I'm going to write as 7I. Okay, now our last one here, we're going to put a little star by this one because this one, although it looks simple, is a little bit tricky. Okay, you need to pull your eyes out first. You need to say, all right, well, the square root of negative 2, that's going to be negative 1 times 2. And then the square root of negative 6 is going to be negative 1 times 6. So this is going to be I square roots of 2 times I square roots of 6, which becomes I squared times the square root of 12. Now 12 can be broken down into 4 and 3. And we know that if we take the square root of 4 and simplify it, that becomes 2. We also know that I squared is negative 1. So we end up with negative 1. And then if we do this, square root of 4, square root of 3, we end up with negative 1 times 2 times the square root of 3, or negative 2 square roots of 3. Okay, this is the correct answer. But I want to add a little something else here. This is not the square root of negative 2 times negative 6. Okay, we can't combine those. We have to pull the i's out first, because if you multiply negative 2 times negative 6, that becomes a positive 12. But in doing that, you're losing that square root of, that I squared that you end up pulling out, which becomes a negative 1. So you're losing that factor of negative 1. You have to account for that negative 1 and pull it out and call it I before you can simplify. Okay, you can't bring those square roots together, which is a little different than what we would think about when we're working with radicals. But when there's negatives underneath our radicals, the rules are a little bit different. So just keep that one in mind. That's kind of a special case situation. Complex conjugates. If the complex number z is a plus bi, then the number a minus bi is the complex conjugate. So for example, if we want to find the complex conjugate of 5 minus 2i, then that would be 5 plus 2i. So we call it the a term and the b term stay the same. It's just the sign that changes. So in the next example, they're asking us to FOIL two conjugates, 7 plus 4i and 7 minus 4i. So we can do that math quickly here. First outer, inner, last. 7 times 7 is 49. My outers, 7 times negative 4i is negative 28i. My inners, positive 4i times 7 is positive 28i. And then my lasts, positive 4i times negative 4i is negative 16i squared. Well, now as you can see, my inners and my outers cancel. So I have this 49, but I squared is negative 1, so this becomes negative 16 times negative 1, which is positive 16. So I end up with 49 plus 16, which is 65. So what happened here with our inners and our outers canceling, that's always going to happen when you FOIL complex conjugates. So really, when you FOIL conjugates, you only need to multiply the F and the L of the FOIL process. So you don't really have to do FOIL, you just have to do FOIL. Little math joke there. All right. Our next example here, 6 over 2 minus 3i, we are going to multiply the numerator and the denominator by the complex conjugate of the denominator. So this is how we rationalize a denominator that has an I in it. I don't have enough room here to do this, so I'm going to go ahead and add a page, and I'm going to do this problem on the next page. So if we have 6 over 2 minus 3i, first thing we're going to do is we're going to multiply the top and the bottom by the complex conjugate of 2 minus 3i, which is going to be 2 plus 3i. Now, the most common mistake that students make on a problem like this is they multiply top and bottom by the exact same binomial instead of multiplying by the complex conjugate. So please, please, please make sure that when you do this, that you're paying attention and that you are changing the sign and you are indeed multiplying by the complex conjugate. Okay, so the step here that we're doing is rationalizing our denominator. So on the top, this is just going to be distributive property. 6 times 2 is 12, and 6 times 3i is going to be 18i. On the bottom, we just talked about how when you FOIL complex conjugates, the inners and the outers cancel. So we're just going to skip that. We're going to do first times first. 2 times 2 is 4. And then we're going to do last times last. Negative 3i times positive 3i gives me negative 9i squared. But again, this is really negative 9 times negative 1, which gives us a positive 9. So we have 12 plus 18i over 4 plus 9. And that becomes 12 plus 18i over 13. Since we have a 13 on the bottom, which is odd and prime, we can't do any reducing. But keep in mind, if that 13 were an even number, then we could reduce the 12, the 18, and whatever the denominator was all by 2. So you can do some reducing with these conjugate problems. You just have to make sure that when you reduce, you're reducing all 3 of your whole numbers in your expression by the same quantity. Our last 2 examples here are going to deal with equations that are going to have imaginary solutions. So we're just going to solve these algebraically and we're going to see where the math takes us. In example 1, since we only have an x squared and a constant term, we don't have an x term, we don't need to solve this by factoring or the quadratic formula. We can just use square roots. So the first thing I'm going to do is I'm going to subtract 50 from both sides. So this is going to give me x squared equals negative 50. Now, next step is going to be to square root both sides. So I'm going to square root x squared, and I'm going to square root negative 50. I get x equals, now don't forget this is an equation, so this is where we definitely need that plus or minus. And now we need to think about how we're going to break 50 apart. Well, the negative is going to get pulled out, the negative square root of 1, or excuse me, the square root of negative 1 will get pulled out and we'll call that I. But then we have to consider 50 and any of its perfect square factors. 25 goes into 50 twice. So I'm going to split 50 apart into square root of negative 1, square root of 25, and square root of 2. So my answer then is going to be plus or minus. Square root of 25 becomes 5. Square root of negative 1 becomes I. And then square root of 2 is going to stay square root of 2. And this is going to be my final answer. I do have 2 solutions. They're both imaginary. In my next equation, 2x squared minus 2x plus 3, I might try factoring this, but what you will find is that it is not factorable. So if I want to solve it, my best bet is probably going to be either, well, completing the square of the quadratic formula. And since a is not 1, I'm going to opt for the quadratic formula. My a value is 2, my b value is negative 2, and my c value is 3. So plugging this into the quadratic formula, x equals, big fraction, opposite of b, so positive 2, plus or minus the square root of negative 2 squared plus negative 4 times 2 times 3, all over 2 times 2. And then I begin to simplify. 2 plus or minus the square root of 4 plus negative 4 times 2 is negative 8 times 3 is negative 24. All over 4. 4 plus negative 4 is going to give me a negative 20 under the radical. And then I'm going to do what I would normally do. I'm going to try to simplify that. I'm going to pull out the perfect square factor, which is 4 times 5. I'm going to pull out the negative 1, and I'm going to call it I. So this is going to become 2 plus or minus 2i square roots of 5 all over 4. And then as a final step in this problem, I can do a little simplifying because 2 and 4 are all divisible by 2. So my final answer is going to be 1 plus or minus I square roots of 5 over 2 when I reduce.